Well, thanks everybody for coming today to this webinar. Thank you for clustering, reducing the cost of wildlife disease science. My name is Chris Rhoda. I am the chair-elect of the Biometrics Working Group. And before I pass things over to Brenda, what I'd like to quickly do is promote the Biometrics Working Group, tell you all a little bit about us, and give you guys information on how you might learn more about our working group. So the goals of the biometric working group are to facilitate exchange of information regarding application of quantitative methods in research and management of wildlife resources and promote proper study design and analysis. That is our goals in brief. What I'm going to do is put our working group website onto the chat now. And for those interested in learning more about who we are and our objectives, you can visit the website. We are a diverse group, and our members span all career stages. Anyone with an interest in wildlife biometrics is welcome to join. And we'd like to continue to expand and connect with early career scientists. We aim to keep the group accessible, and our membership dues are only $5. So hopefully that makes it accessible for anyone that wants to join the group. To achieve our goals, a lot of our activities revolve around hosting biometric-centered symposia and workshops at the annual meetings, and hosting such workshops between meetings at events like these. We also host conference events like Ask a Biometrician, facilitate roundtable discussions related to emerging issues in wildlife biometrics, and much more. In particular, we seek to promote students and early career professionals with an interest in biometrics, and we do award a lot of conference travel awards to students who are presenting biometric center talks and posters at the annual conferences. Finally, you can connect with us via our listserv. You don't need to be a biometrics working group member to join our email list. And you can join that in two ways. One, and I'll put a link on the chat for this one, is to go to the Google Groups site. Go to the Google Groups site, and once you're there, click the join button. Or you can send an email to our secretary, Laura Gigliotti, and I'll post her email into the chat as well. And if you tell her that you want to join the Biometrics Working Group website, Biometrics Working Group listserv, she'll sign you up as well. And pardon me while I put that into the chat. Okay. Right. And with that, I would like to hand it over to Brenda Hanley, who will be hosting today's webinar titled Thank You for Clustering, Reducing the Cost of Wildlife Disease Science. With that, Brenda, I'll hand things over to you.
Okay, thank you. Let me share my screen. Okay, you guys can all see that. All right. Good morning or afternoon, depending on where you are. My name is Brenda Hanley, and on behalf of a large interdisciplinary group of wildlife health professionals and statisticians, I would like to present how to leverage clustering to reduce the cost of wildlife health investigations. The path to this research has been super interesting, so let me tell you its story. A few years ago, some of us were tasked to take necropsy information collected from opportunistically samples and make inferences at the population scale. Now, statisticians generally use random data to make inferences at the population scale, but we didn't have that. Epidemiologists skirt this issue by limiting inference to a smaller population or by creating randomized controlled trials. But in wildlife health, countless limitations mean we can't execute randomized designs. And the entire population scale and nothing smaller is the scale of interest to wildlife managers. So we were stuck. In our minds, there was a fundamental statistical disconnect between our data and our question, and we certainly did not know of any methodological tools to span that gap. Enter SOP for CWD. We began the Surveillance Optimization Project for Chronic Wasting Disease as a grassroots approach to tackling urgent quantitative topics in wildlife health. Since the project began, over 20 state wildlife agencies have voluntarily joined and shared their data. We have also gained tremendous strength as a quantitative group representing academic institutions and government agencies across North America. We have accumulated over 1 million data points on CWD alone, and all tell the same story. We have gobs of opportunistic surveillance data and sometimes convenience data, yet the questions we want to answer lie squarely at the population scale. So it became clear, bridging the gap between the individual scale and the population scale is the quantitative crux of the entire field of surveillance in wildlife health. Our quantitative group got to work. We have many questions left to answer, but we have answered a few. One that we have answered involves a new sample size calculator. This calculator addresses a foundational investigative goal in wildlife health surveillance. That is, to tell us how many samples we must test to rule out disease in a greater free-ranging wildlife population. You might be thinking that this question has been addressed and other sample size calculators exist, and you would be right. But those calculators do not explicitly consider that wildlife subjects are not taken randomly. Further, those calculators do not consider that hosts cluster on the landscape, which is nearly ubiquitous property of free-ranging wildlife. To develop our sample size calculators, we took a totally new approach to sample size computations, with the explicit goal to make the tools relevant to practitioners of wildlife health. And what we found has astonished us. As we plowed further into this topic, we discovered that we can leverage clustering tendencies to garner more information out of fewer tests. As you will see in this presentation, clustering of hosts naturally enhances sampling efficiency and allows us to take wildlife health information up to the population scale more efficiently. Today, I will showcase our two apps and discuss the concepts underneath. Both apps are published online and free to use. I will show each in turn, give examples, and then show you where to find them. Our first app allows you to compare sampling sizes under simple random sampling, with and without host clustering and correlation. The second app allows you to compare sample sizes in the presence of clustering and correlation across 3 different sampling schemes. You will learn a lot of things that will warp your mind today, and welcome, this entire body of work has warped our minds too. The first thing that you will learn is that clustering reduces the number of animals we need to test to make inferences about disease freedom at the population scale. The second thing that you will learn is that it is easy to unintentionally wipe out those savings by the way we procure animals from the landscape for disease testing. And the final thing you will learn is how to strategically work in concert with this natural benefit to squeeze the most information out of your limited sampling dollars. Led by Dr. Booth of Cornell University, this body of work uses a Bayesian framework to compute the sample sizes needed to declare a population free from disease. But the novelty of this math is that it explicitly considers host clustering and correlation in disease status among hosts sharing that cluster. We will talk about the concepts of cluster and correlation next. But before we do, I want to point out that this work is sufficiently theoretical such that it applies to nearly any disease host system. The theoretical equations are published in the Journal of Agricultural, Biological, and Environmental Statistics and the Journal of Wildlife Diseases, and both can be accessed using the QR codes on the page. In this presentation, I will not show many equations, but instead focus on the concepts and the corresponding software. I warn you that nearly everything that you're going to learn today is counterintuitive, so buckle up. The clustering and correlation are key concepts of this new sample size calculator, so let's define each. A cluster is a group of hosts whose members share disease status. A cluster can come about in several natural ways. The most obvious cluster is a family or social group. Here, disease is transmitted more readily within groups than across groups. Examples are endless across the animal kingdom: herds of deer, flocks of birds, etc. This definition could expand beyond wildlife to cows in a pasture or children that share Miss C's fifth grade math class. A cluster can also be the group of hosts that overlap in a disease reservoir. For example, the set of deer that travel over some prion contaminated agricultural field, or the set of beavers that share some common waterway. There exist more obscure definitions of clusters. A cluster can also be the set of hosts impacted by a single disease host. For example, a mosquito carrying heartworm might be more likely to bite two wolves within the same pack than a wolves at the opposite sides of a mountain range. Or a cluster can be the set of scavengers that ate off the same diseased carcass. The boundary conditions on cluster size is 1 and big N, where big N represents the size of the population for inference. A wolverine is a great example of a single host, a single cluster. This guy is a pretty much solitary year-round. When we have one host per cluster, then the number of clusters is equal to big N, and there's no need to consider correlation. Alternatively, an entire population can form a single cluster. Think of those huge colonies of penguins. Here, we might as well draw the boundaries around the entire population and call it a single cluster, because after all, everyone is interacting with everybody else. In this case, we have one cluster, and the cluster size is identical to your big N, the population size. Your population of interest can constitute one cluster with many subjects, many clusters with few subjects, or anything in between. Think of clusters as natural subsets of the population of interest in your disease investigation. Since the concepts are intertwined, it might be helpful to think about correlation in disease status when defining your clusters. If you think clustering is slippery, the definition of correlation is even worse. Correlation is the relatedness in disease status among hosts sharing a cluster. Think of correlation as the function of disease as it relates to the clustering in your population. But what does that even mean? Let's start with the easy part. The boundary conditions on correlation are 0 and 1. When correlation is 0, hosts within a cluster incur disease independently in our model. Alternatively, when correlation is 1, all hosts sharing a cluster simultaneously have the disease, or they don't. Easy, right? But it's harder to understand the middle in-between stuff. In fact, correlation is an active area of research by our group with additional mathematical details forthcoming. While it has something to do with R naught, the relationship is not super obvious. But we are working on that, and we have several grant applications out to fund that exact research. For now, assume correlation is subjective, parameterized by expert opinion, and based on the combination of contact and transmission of the disease in the host system of interest. Now let's try to visualize correlation to get a better feel for this property. Okay, picture in your mind's eye a child blowing bubbles. Bubbles can take on many forms. They range from a bunch of completely round spheres to a large 3D globs of smooshed blobs that stick to the ground. Okay, you following me so far? I want you to think of correlation in disease status among hosts sharing a clusters as bubbles with varying degrees of clustering and smoosh. When we have 0 correlation, we have a bunch of bubbles without any smoosh. The bubbles are not touching. In terms of disease in our hosts, there is no overlap in disease status. It makes no difference that the hosts are positioned together in time or space because each host is independent of the others. When correlation is 0, the more subjects we test, the more information we get about the disease. This is the math of historical sample size calculators. More tests equals more information. Now think of our bubbles starting to smoosh together. They are now touching. They form a distinct cluster, and they are sharing edges. Here, clustering matters because each bubble is now loosely connected to the others in the cluster. In terms of disease in our hosts, once a disease is introduced anywhere into this cluster, it can spread more easily to all the hosts within the cluster. For example, think of a family group of humans that get the flu. When we have low correlation, knowing the test result of any host in this cluster tells us about the disease status in that host, but it also gives us some clues about what is going on in the rest of the cluster. Now think of disease with high correlation. Here, our bubbles have smooshed together into an amorphous blob, and it is really hard to see individual bubbles. Here, little individuality is present. In terms of disease, think of mange in a den of foxes. Once the mites enter the den, it's only a matter of time before every last fox in the den is infected. When we have high correlation and test one of the hosts, we get lots of information about the entire den. And finally, perfect correlation. Perfect correlation means that individuality has vanished and only a single shared blob remains. Perfect correlation means that when we test one host, we get all the disease information about the entire cluster. You are likely picking up on the pattern that the higher the correlation, the more disease information that we can get from a single targeted diagnostic test. But how the population is clustered really complicates that. In fact, depending on clustering, more tests do not always lead to more information. Let's walk through a toy example involving duck viral enteritis, or DVE, in mallards. While we have 24 additional real-world examples in the software that I will discuss later, I chose this example simply because I like the photo. But the math is invariant to the system, and that's the take-home message. The logic applies to nearly any host in the animal kingdom. We will start by examining a single cluster of mallards, then expand that to an entire population. Here is our cluster of mallards. Due to the contact structure of this cluster and the transmissibility of DVE, we estimate the degree of smooshing, the correlation, to be 0.3. Because there is not infinite free photos of bubbles on the internet, let this very poor 2D graphic stand in for a 3D concept that we just learned of overlapping clusters. So bear with me with these schematics. For simplicity, think of DVE as a 30% overlap in disease status among mallards sharing a cluster. Let the orange circle represent the first mallard selected for DVE testing, and let the blue circles represent the remaining mallards sharing the cluster. It doesn't matter the position of this selection within the cluster. I drew it in the middle just for ease. We will next find the disease information content at the population scale when we test 1, 2, all the way up to the 6 mallards in the cluster. We define disease information content as the per duck contribution to inference at the population scale. A way to define units of disease information uses the variance of the sample sum in the uncorrelated case relative to the correlated case, all relative to the size of the cluster M and the correlation R. Here and in everything that follows, I'm going to stretch your mind to think of sample sizes in terms of units of disease information at the population scale, as opposed to the traditional way of thinking about sample size in only the number of hosts tested at the individual scale. When the first mallard is tested, we apply the formula with m equals 1 and r equals 0.3. We find that we get 1 unit of information out of that test. One test, 1 unit of information about DVE at the population scale. When the second mallard is tested, we apply the formula with m equals 2 and r equals 0.3. So now we have paid for 2 tests, but we have only accumulated a total of 1.5 units of disease information at the population scale. Same with the third mallard. We've now paid for 3 tests, but we have accumulated 1.8 units of information at the population scale. As you can see, when we sample more and more animals from the same cluster, money spent is multiplying linearly while there are diminishing returns happening regarding new information about DVE. Let's keep going. We now use m equals 4 and r equals 0.3, and we get 2.1 units of information. So we've just paid for 4 tests, but we've gotten only 2 units of information out of those. As we keep testing within a cluster, our costs keep accumulating at a rate much higher than the accumulating information on DVE at the population scale. And finally, we've exhausted the cluster. We've paid to test 6 ducks, but we have gained 2.4 units of total information about DVE at the population scale. Herein lies the key observation of this math. The cluster has 6 ducks, which means to test them all, we need to pay for 6 tests. But when we do that, we only amass 2.4 units of information about DVE because all those ducks were related in disease status. If we want to accumulate inference about disease freedom at the population scale, repeated sampling within the same cluster is inefficient. It is inefficient for this investigational goal because we are paying over and over for information we already know. Now expand our minds from one cluster to a population of many clusters. Suppose our population of mallard contains 5 clusters. This means that we have 30 total ducks, but only 12.5 units of available information about DVE at the population scale. How many samples must we take to achieve 95% probability that DVE in our mallard population is at or below 1% prevalence? We can investigate this question using our first sample size app. This app allows us to compare sample sizes in the presence and absence of correlation and allows us to pinpoint the number of hosts we need to have high probability that the entire free-ranging population is disease-free. The app is live at the link and you can access it at the QR code on the right. The code is also shared openly with an MIT license and available at the citation at the bottom of the slide. When you enter the app, the first entries you are asked to provide are your total population size and average cluster size. Due to the estimation of sample sizes needed for a 1% disease prevalence, the smallest population size you can enter into the app is 100 hosts. Cluster size is assumed to be fixed where every cluster is identical and of the size you enter. The second tab allows you to enter your within cluster correlation. Because this parameter is modeled as a beta binomial, the app draws an example of a beta distribution that is relative to your inputs. There is also a tab for sampling scheme, but in this app, only simple random sampling is the option. The next tab allows you to enter the sensitivity of your diagnostic test. The sensitivity is the test's ability to correctly identify the disease when it is indeed present, or in other words, a true positive. The fifth tab allows you to enter the number of runs to use the simulation. The number of simulations matters for runtime. Lower simulations gives faster runtime, but more imprecise estimates on sample size. As an aside, if you want to run the simulation with 10,000 or more iterations, I recommend downloading the raw code out of eCommons and running it on your local machine, as opposed to overloading the online Shiny application. Once all your parameters are entered, you will launch the calculation and wait until the spinner is done spinning. 2 graphs will appear that show the sample sizes with and without correlation. On these graphs, the x-axis represents the sample size and the y-axis represents the corresponding probability of that sample size. The triangles reveal the sample size needed to have 95% probability that disease prevalence in the overall population is at or below 1%, the yellow line, or 2%, the red line. You will also find information on the sample savings in the presence of correlation at the bottom of each slide. Let's demonstrate this simple app with our familiar mallard example. Suppose we have 6,000 ducks in our population divided into clusters of size 6. Correlation of DVE is still 0.3. Let's use a diagnostic test sensitivity of 99% and run about 5,000 simulations. The app takes about 10 minutes to run and produces the graphs above. According to the app, we need 278 ducks to test negative for DVE in the presence of correlation and 289 ducks in the absence of correlation to achieve 95% probability that DVE in this population is at or below 1%. Correlation gives us a natural sample savings of 4%. If we don't particularly care about 1% prevalence and can settle for ruling out 2% prevalence, then we could test 141 ducks with correlation as opposed to 148 ducks without correlation. This produces a 5% savings in sample size. A savings of 4 or 5% might seem pretty small, but that's just the situational result in our duck population, given the specific configuration that we used in the app. Savings can be dramatically higher. In fact, it was pretty illuminating to make over 30 real-world tutorials because we found an astonishing variety of sample savings. The largest savings occurred when cluster size was large, correlation was high, and test sensitivity was high. This is like investigating white nose syndrome in a single cave of bats. When we used real-world numbers for all of our parameters, we discovered an astonishing savings of 88%. An 88% discount is real cash money and quantifiable on any budget sheet. But if we need to handle 88% fewer animals, that also limits exposure of biologists to disease as well as potential spillover events, both of which are priceless to individuals as well as to society. I encourage you to pore over the examples and see the variety of savings. You can find them by clicking on the tutorials button at the bottom of the sample size app. Of course, feel free to play with the app to see savings within your own disease host system. An important note is that this first app finds sample savings under simple random sampling only. But we also know from this body of work that sampling scheme matters. So let's dig into that. Recall that we expanded our minds from thinking about one cluster to thinking about population of many clusters. Recall also that in our example mallard system, we had 5 clusters, which means we only really had 12.5 units of available information on DVE. How can we sample from the population to obtain the most units of information on DVE with the fewest number of ducks taken from the landscape? We can answer this question by finding the expected value of the disease information content under 3 distinct sampling schemes. For simplicity, let's say we want to collect a sample of n equals 5 ducks. We will first compute the expected value of the information content at the population scale arising from simple random sampling. We will then use high harvest sampling, then finally 2-stage cluster sampling approaches. In this demonstration that follows, you will see that the scheme used to collect hosts from the landscape dramatically influences the information content of our resulting data, even with the same number of ducks taken from the ground. Let's start with simple random sampling. As you know, in simple random sampling, every sample of size n has the same probability of being selected. While simple random sampling is a long-used scheme in traditional statistics, simple random sampling has been largely abandoned in wildlife health investigations due to its pragmatic limitations. It does not accommodate the fact that wild animals have differential geography, that we have differential access to them, must abide by various regulations or collection ethics, or even that we may have selection biases. Simple random sampling is purely a probabilistic way to select subjects from a population such that the resulting subset can be used to make inferences about the whole. For completion, we will address this first as our statistical baseline. Turns out there are 7 possible ways to take 5 mallards out of a population of 30, which has been compartmentalized into 5 clusters of size 6. We can take one sample from each of the 5 clusters for a total n size of 5. We can take 5 from the same cluster while ignoring the other 4 clusters. This also results in an n size of 5. Or we can take any combination in between, provided it results in an n size of 5 birds. Also of note, while I have written these groupings in shorthand notation, we are dealing with combinations, not permutations. Okay, for those of you who love doing math by brute force, this is the problem for you. I'm not going to go through each step in the computation of expected value. Just know that each scenario has an outcome, which we define to be the total information content at the population scale arising from how we collected the 5 samples on the ground, and a specific number of ways that outcome can occur, which is a huge exercise in combinatorics. Only one of the outcomes is depicted in the schematic on the right. Remarkably, even with a population size as small as 30 mallards, there are an astonishing almost 150,000 ways to get a sample of 5 ducks. So here we go. The first scenario has all singletons. This is where we get 1 duck per cluster. When this happens, we'll obtain 5 units of information. There are 7,000 ways to achieve this. This scenario produces 5 units of disease information and will arise by chance 5% of the time. The second scenario consists of 1 pair and 3 singletons. We can achieve this outcome nearly 65,000 ways. This scenario produces 4.53 units of disease information and occurs by random chance 45% of the time. You can see where this is going. We do the same process for each of the 7 scenarios. But like those YouTube videos where someone puts a casserole into the oven and then takes it out hours later, we will spare you the details and skip to the end. Finally, we have arrived at the 7th scenario, which has all 5 ducks taken from the same cluster. Here, there are 30 ways to get this outcome. This scenario produces 2.27 units of disease information, but happens by chance less than 1% of the time. That is, it's exceedingly rare. Multiplying each of the 7 outcomes by its corresponding probabilities gives us the expected value of disease information content at the population scale arising from 5 samples. We find the expected value to be 4.26 units of information on duck viral enteritis. Let's look at this in perspective. We've sampled 16% of the total hosts in the population and obtained 34% of the total disease information. This is great news. We have doubled the information content on disease relative to the number of hosts tested on the ground. This result is one example of how correlation increases the information content per test. Accordingly, correlation can reduce the number of hosts we need to declare an entire population disease-free. As it turns out, when correlation is present and the cluster size grows, so does the information content from a single diagnostic test. Let's see if we can investigate the details of this expected value to unlock additional sample savings. This graph shows a summary of all 7 outcomes in our mallard example. It contains the probability of each scenario on the x-axis and the corresponding information content gleaned from 5 ducks on the y-axis. The dotted line at 4.26 is the expected value of the disease information from our n equals 5 samples. If the sample of mallards is purely drawn at random, an investigator will most likely get 1 pair and 3 singletons. This results in slightly above average information content and occurs 45% of the time. The highest information content comes when all 5 samples are singletons. However, this scenario only occurs by chance about 9% of the time. Nevertheless, we call this the information-rich scenario. As more and more samples are taken from fewer and fewer clusters, the information content plummets. We call these the information poor scenarios. The worst scenario occurs when all samples are taken from the same cluster. This scenario gives us the least information at the population scale. But if the sampling is purely random, then getting this result by chance alone is super rare. It occurs naturally less than 1% of the time. But notice, widespread current practice in wildlife health is to obtain tests opportunistically, which often results in multiple tests taken from the same handful of the most accessible clusters. This action may increase the likelihood that this information poor outcome occurs way more than 1% of the time. Which leads us to high harvest sampling. High harvest sampling was a term coined by Belsar et al. In the prior work on sample sizes needed to investigate chronic wasting disease in cervids. Here, we expand this term beyond harvest. Here, we allow high harvest sampling to be any sampling that involved taking lots of hosts from a few of the most convenient clusters. In high harvest sampling, if a host is near humans, situated by a trailhead or access point, in a hayfield behind someone's house, killed by a vehicle on the road, etc., then it is likely sampled for disease. Alternatively, if the host lives way out in the wilderness, it technically can get sampled, but it is not very likely. I will show you next why it is so hard and sometimes even impossible to convert information from these samples to disease inference at the population scale. Let's return to our familiar example in mallards to find the expected value of the information content of the same 5 tests under high harvest sampling. Let's start with the narrowest focus on clusters. Here we obtain 4 ducks out of the single most convenient cluster. We get that last duck from some other remote lake. The expected value is 1.52 units of disease information at the population scale. Let's put this into context. We just paid to sample 16% of the hosts in the population and got 12% of the disease information. And correlation is in these equations. So even with the natural benefit of correlation, we aren't even breaking even. For better or for worse, convenience has limited our pathway to scientific inference at the population scale. Now let's suppose there are 2 convenient clusters of mallards. We get 4 samples from those, plus the random duck at some remote lake. Our expected value of the disease information content is now 2.51. This is getting better. We have sampled 16% of the host and gotten 20% of the information, which means that we are breaking even and unlocking the benefits of correlation. But we are still not doing as good as we can with the same 5 samples. Let's keep expanding our sampling to more and more convenient clusters. Now we get 4 ducks out of the 3 most convenient clusters, plus the random duck from the wilderness. Our expected value is 3.19, which is getting much better. Finally, let's assume all but 1 cluster is convenient. We get 4 ducks from these, plus the final random one way out in the wilderness. Under this scenario, our expected value is 3.59. If we go up any more, we are back to sampling all 5 clusters. So let's stop here and summarize what we just learned about high harvest sampling. As randomness is abandoned for convenience and sampling is funneled into fewer and fewer clusters, we keep paying for tests, but the information content at the population scale plummets. Narrowly focused high harvest sampling can be the most inefficient type of sampling of the 3 types that we evaluated, because we inadvertently wipe out natural savings from correlation. Plus, we pay over and over for information we already know. But look, we can get close to baseline efficiency, even with convenient selections of clusters, provided we sample from as many clusters as logistically possible. Let's move on to our third and final sampling type. 2-stage cluster sampling is similar to high harvest sampling in that we sample hosts from a subset of all the clusters. But unlike high harvest sampling, we select the clusters themselves at random. This means that the cluster by the trailhead and the cluster way out in the wilderness are just as likely to be selected for disease sampling. Another key point with 2-stage cluster sampling is that if a cluster is not selected for sampling, then its hosts are ignored, even if they're convenient. Okay, you know the drill. Same process of finding the expected value. Let's randomly select all 5 ducks from a single cluster. Whoa! The expected value of disease information content under this scenario is 2.27. That is hugely different than when we sampled a single cluster for convenience. In fact, we have already broken even and gotten some benefit from clustering. This shows that randomness really is important for maximizing disease information content at the population scale, even when fewer clusters are sampled. Now let's calculate the expected value under 2 randomly selected clusters. The expected value is now 3.32. We're ahead in the information game with the same 5 samples. We have sampled 16% of the hosts in the population and obtained 26% of the information on disease. Randomly sampling 5 ducks out of 3 randomly selected clusters gives us an expected value of 3.82. As you can see, we are truly unlocking the benefit from correlation. And finally, let's get all of our samples from 4 randomly selected clusters. This is great. We have doubled our information content with the same 5 samples. We are almost as good as simple random sampling, even with ignoring a whole cluster. But if we go up any further, we're back to sampling all 5 clusters. So let's stop here and recap yet again. Again, we see that as sampling is funneled into fewer and fewer clusters, the information content at the population scale decreases. Purely random sampling is still the best for efficiency, but there are some situations where limiting clusters might help managers in the real world. We can afford to miss a limited number of randomly selected clusters without seriously jeopardizing information content, provided we still sample from as many clusters as logistically feasible. Let's compare all 3 schemes side by side for our mallard population. We find that the more distorted the sampling distribution, the less information is gained from the same number of tests at the population scale. Here, a distorted sampling distribution is one that puts too much emphasis on too few clusters. Also notice that when we abandon randomness for convenience and only focus on a few clusters, then that is the least efficient way to obtain information we need for inference at the population scale. In fact, take a look at that. We keep spending testing money, but we aren't even breaking even. In the worst case, which we will touch on later, we can test and test and test into eternity and may fail to gather the information we need to ever make declarations at the population scale. So you might be thinking, okay, so this is simple random sampling containing 30 mallards. What about my disease host system? Which brings us to our second app. Called the Efficient Sample Size Calculator, this app also considers the clustering and correlation of your disease host system, but unlike the first app, it adds the ability to compare sampling schemes. It also adds standard errors on sample estimates and a slew of interpretations to help us understand our sampling designs. The live link is displayed on your screen, or it can be accessed by the QR code on the right. The citation and persistent DOI for the code is at the bottom of your screen. In this app, you first enter the population size and cluster size, but here you can also parameterize your clusters to be fixed or random. If random, cluster sizes are drawn from a Poisson distribution with the cluster size as the parameter. The graphic at the bottom of the page illustrates your entries so you can visualize how your population is partitioned into clusters. Recall the boundary conditions on cluster sizes. If your cluster sizes jive with your population size, then the app allows you to advance. If they don't, it won't let you go forward. It will tell you the problem and how to fix it so you can really visualize what you're typing in. The next page contains the sampling scheme. Each time you enter a sampling scheme, a schematic will appear that shows you what that scheme means in the context of the population and cluster size you entered in the previous tab. Here's the graphical representation of simple random sampling. Here is the page you see if you select high harvest sampling. The conditional sliders appear at the bottom of the page, which allows you to parameterize how much emphasis you want to place on how few clusters. The graphic in the middle is reactive to those settings and allows you to visualize what those entries mean in the context of your population and clustering configuration. And finally, Here's the page when you select two-stage cluster sampling. Again, the graphic is reactive to your inputs. An important note is that when you choose high harvest sampling or two-stage cluster sampling, the boundary conditions on available narrowness changes relative to your configuration. After all, you cannot take more samples than there are hosts in those clusters. If your settings do not satisfy these basic properties, then the app won't let you advance. The next tab allows you to enter your prior on correlation with a graphic to help you interpret the number. You can also enter your diagnostic test sensitivity, after which a graphic shows how that sensitivity performs in declaring a true positive. You are then asked to enter the desired number of runs for the simulation. Lower is faster, but produces less precise estimates. When you arrive at the end, you will see a button to launch the calculation. A progress bar will appear while it is running. When the simulations are complete, a graph will appear showing the sample needed in the configuration used. The exact parameters are reiterated below the graph. As an aside, the configuration that I randomly typed in to get this screenshot resulted in sample sizes that go flat, meaning that we can sample for eternity and never achieve 95% probability. I teased you earlier that this result could happen, and here it is. Sample sizes that go flat cut directly against our widespread intuition that more sampling is always better. Indeed, if our sampling scheme that we use on the ground effectively shifts from information poor outcomes being rare to information poor outcomes being the most common, then we can test and test and test and never make it up to the population scale. We will talk about that more later. Let's use the second app with our familiar Mallard example to compare sample sizes across different sampling schemes. We use the same parameters as before, but focused our sampling to a narrow band of clusters. I created this slide by running the app 3 times, one with each sampling scheme. Simple random sampling appears on the left, high harvest in the middle, and two-stage cluster on the right, all with identical parameters. Without correlation, we recall that we need to test 289 ducks. With simple random sampling, we need to test 275 plus or minus 4 ducks to rule out disease at the population scale. But when we look at high harvest and two-stage clustering sampling, we find no savings. In fact, we have inadvertently wiped out savings from correlation, plus added many more required hosts due to our reliance on information-poor samples. This is just one example with the disease with one host population. Not all examples are this egregious. Some examples give the 3 sampling schemes as super close, and some are astonishingly different. Some schemes get you up to the population scale in a hurry, while others go flat. There is a huge range in possible outcomes. Results hinge on the configuration used, and sample savings may exist, may not exist, may be little or may be large, depending on that configuration. The only way to truly know what the sample size or scheme is best for your specific system is to investigate it using real numbers. Feel free to use these apps to help you do exactly that. Like the first app, the second app also has a ton of real-world examples using combinations of cluster and population sizes, high and low correlation, and high and low sensitivity. As I touched on before, and what you will notice when you pour through these examples is that sensitivity is a surprisingly influential factor. The lower the sensitivity of the diagnostic test, the easier it is to wipe out sample savings from natural correlation structure. I like to think of the complication of sensitivity like destructive interference. When 2 interfering waves meet, they tend to cancel each other out. Alternatively, the best case for sample savings occurs when high correlation exists among high sensitivity. I think of this as constructive interference. 2 complementary waves adding into a monster wave. This is great for savings. But sometimes savings is just chaotic. In addition to additional research on correlation, we are also on the path to finding the bifurcation points of where outcomes dramatically change course with minimal changes to inputs. Anyhow, take a look at the examples tab to find all those tutorials. And of course, try the app yourself with your own system in mind. Okay, we have learned a lot today. And if your brain is smoking, then welcome, because ours is too. Okay, so let's recap the take home messages from this massive body of work. Correlation in disease status reduces the number of animals we need to test to make inferences about disease freedom at the population scale. But if our focus on clusters is too narrow, or worse, if we simultaneously only take samples of convenience, we can easily wipe out those savings. Or we can work with this natural benefit of correlation by using a broadened focus across many clusters to achieve the most efficient sampling strategy possible. The best sampling strategy for inferring disease freedom at the population scale generally involves testing a limited number of hosts from as many clusters as possible. The best strategy also involves randomness. After all, the likelihood of getting an information poor scenario under simple random sampling is vanishingly small. But we recognize that sampling wildlife disease is wrought with real-world complications, and we must be pragmatic. We know that geography, land access, ethics, regulations, cultural practices, or even host selection biases all collapse into the myriad decisions of why certain animals are taken from the landscape for tested and others are not. So if, for whatever reason, we can't achieve one host per cluster as well as randomness, then the next best sampling strategy involves gathering one host per cluster, even if that animal is selected non-randomly. This way, we maximize the information content of each test to the highest extent possible. One way to get one host from each cluster is to collect only animals from unseen clusters, or by post-stratifying records into clusters based on geography or some other real-world biological metric that is directly related to the definition you used in your clusters. This math has shown us that if our goal is to make inferences at the population scale to the greatest extent possible, we ought to avoid repeated sampling for disease within the same cluster. We should also try to avoid putting too much emphasis on a narrow few band of clusters. When animals are clustered, more tests do not always equal more population scale information. Let me say that again because it is so counterintuitive. When animals are clustered, more tests do not necessarily equal more information about disease at the population scale. Unless the goal of sampling is some other investigatory reason in wildlife health, there is no benefit to exhausting a single cluster. Indeed, several examples in our app, including one on the earlier slide, show that when we focus all our sampling on a few number of clusters, we can sample forever and still never achieve 95% probability that the disease is at or below 1% if in the greater population. And as if this is not all complicated enough, enter the complications from diagnostic sensitivity. If sensitivity is too low, it is possible to literally exhaust an entire cluster and maybe even an entire population, that is to take a census, and still never achieve 95% probability that disease is at or below 1%. How can that be? If we have a census, then we have all the information, right? Not necessarily. If test sensitivity is too low, the test itself can be wrong. We think we have all the information, but we really don't. So when planning your sampling design, seriously consider whether a diagnostic test is any good at detecting disease in your host species of interest, especially if it is an obscure or understudied wildlife species. If not, then no amount of clustering can help you achieve your investigatory objective. But above all else, the math suggests that we need to try as best we can to compare sampling schemes before we go out and sample. We really don't want to inadvertently end up with a scheme that uses up all of our testing money and produces information poor outcomes. Use these apps to try to find the scheme that works better in your exact system, given the pragmatic challenges you face in reality. Now, notice this entire time we haven't talked about actual dollar amounts. Given differences in sample sizes or changes in logistics under different sampling schemes, We can do simple calculations with our own finances to answer these budgetary questions, such as, given my system, is it cheaper to use sampling design A? At what point is it better to use sampling design B? At what point does the information poor sampling completely hinder my ability to meet objectives at the population scale, even if it is convenient? If we have learned anything here today, it's that the answer to these questions is not a simple more tests equal more information. We've learned here today that the answer depends on how you sample in the context of the population you are investigating, and specifically the clustering and correlation structure. In the end, our ability to transfer information from individual scale tests up to the population scale starts with the decisions we make in the field. The animals have given us efficiency by clustering, but the rest is up to us. Thank you to the Biometrics Working Group for inviting us today, and to the Wildlife Society for facilitating this webinar. We also like to thank 24 state and provincial wildlife agencies and scores of researchers, too numerous to name, who have participated in the Greater SOP for CWD project. You can visit our SOP for CWD webpage and find bios of our quantitative group using the QR code. We further thank many state agencies, as well as federal entities, including AFWA, U.S. Fish and Wildlife Service, and USDA for funding. With that, I would be happy to take any questions.
Brenda, we do have 2 questions in the Q&A there.
Okay, one of the questions is, the correlation parameter in your beta binomial model seems very similar to the intercluster correlation coefficient using classical survey design and epidemiology to count for clustering and effective sample size. Do you see this approach as conceptually extending that framework, or as something distinct? Is there a reason ICC terminology isn't user reference? I wonder if making this link might help this approach to the broader applied surveillance literature. Yes. So I would love for you to come to our Thursday meeting to ask this direct question of the entire group. And I think that you're absolutely correct that making this link would approach this to the broader influence of surveillance literature. So if you would like to come and ask that of everybody, including Dr. Booth, who is the first author, we can accommodate that, and you're welcome to come over Zoom. Okay, finally, surveys. There it is. Estimate wildlife population size, have confidence intervals. Yes. So would cluster size. Yes, both. Does this app accept and do simulations with these parameters having confidence intervals, or would one need to repeat the simulations using different estimates? Yes. So this has come up in our group so far, and the answer is the latter. So choice B. So right now, if you have different confidence intervals on your cluster size or your population size, you would want to run the app with the minimum, run the app with the maximum, and then combinations of those two to get the overall propagation of error through the app. But you're right, it would be incredibly easy or incredibly good to have like a distribution as a prior on both of those. Right now, we don't. We just have population size as essentially a scalar, and then we've got cluster size as essentially a scalar. We do have a prior on prevalence that has a distribution, and a prior on correlation that also has a distribution, but that's it. There's a lot left to be done. Okay. There's a question of, how does the app converge on the correct prior to posterior distribution? This is a rejection sampler that's going on under the hood. And so that rejection sampler is the thing that creates the posterior distribution. And then what kind of guidance is available on how to estimate the parameters needed in the app? I think how to estimate the parameters needed in the app. So right now, correlation is the one that is the least estimable using mathematical equations. That's the one that we're focusing on right now. any sort of guidance for cluster size and population size, that will come from the biologists. And so as biologists, it will be expert opinion on whether or not you have a good population estimate, and then also on the cluster sizes. Now, an important point is that right now, all of the cluster within cluster correlation assume that every animal within the cluster has the same correlation. And so there's lots of variation there in terms of epidemiology, where there could be disease entered at a certain time and it doesn't have all of the pairwise correlation. So there's a lot of research that can be done on when the disease enters the cluster. Right now, we're just assuming, for simplicity, that every pairwise host combination in the cluster has the same correlation. Okay, and then, yeah, okay, any more questions? I think that I've answered both of those so far. Okay, the question is there a way to test for co-infections to get the best sample size for both or multiple diseases? Or would you use the sample apps for each individually and then choose the best test? Yes, yeah, so choice B again. So right now we don't have anything in there for co-infections for multiple diseases. We also don't have in there for multiple correlations among groups. Which might be the case if you had like two different species that were susceptible to the same disease, but their transmission coefficient might be different. We don't have any of that in there right now. Those are the next obvious steps to put in there, but right now we don't. So as of right now, the answer would be to use each disease individually, and then only, choose the test specific subject. Yeah, there you go. Also, another thing to think about is sensitivity. So because we talked a lot about sensitivity earlier in this, if you have multiple tests that you can use for the same inference, you can also use the test sensitivity with the lowest sensitivity and then use the test sensitivity with the highest sensitivity to get the range of what you would need if you have different diagnostic test sensitivities or different people using different diagnostic test sensitivities. Any more pressing questions? You're also welcome to email me directly, email first author Dr. Booth, or email the SOP for CWD quantitative group with any of these questions. We'd be happy to chat with you on where we are, where we still need to go, what we've accomplished, and everything in between. As you can see, we've got a lot left to accomplish, but this is a really promising avenue for research.